bow and let your arrow go straight to my lover's heart. For me, for me. Cupid, please hear my cry and let your arrow fly straight to my lover's heart. For me. Now, I don't mean.
Howdy, Ags. We are back. You might guess, since we're talking about Cupid and arrows, that it's time to have a short review on vectors. So almost all the variables that we're going to be talking about from now on: linear and angular velocity, linear and angular acceleration, force, torque, power, momentum, impulse. They all are vectors. So what's a vector? Well, vector is usually represented by an arrow, and it has magnitude, size. It also has direction. The longer the arrow, the greater the magnitude, the larger the number. So, for example, a baseball traveling at 40 miles an hour has a vector that's half as long as a baseball traveling at 80 miles an hour. So pretty straightforward. In terms of direction, we usually use the angular reference system. Usually the reference is a horizontal line. Sometimes it's a vertical line. And direction is key. So for example, if we get on Highway 6 and we want to go down to Houston, so we've got some family down there, and maybe we haven't seen them, or maybe for example, we haven't seen maybe a brother or sister or aunt for a while, and we happen to be here in College Station. If you live in College Station, many of you are living down in Houston, so you'd have to turn that arrow around, wouldn't we? We'd have to reverse that vector. But let's say we're here in College Station and we get on Highway 6. We want to go to Houston. The last thing we want to do is turn the wrong way, get on Highway 6 going north, going to Baylor and Waco. So my daughter's in Aggie, just recently graduated, and she'll tell you the thing that Aggies hate most besides Old TU would be Baylor. For whatever reason, they're up there. Try to avoid Waco. So, all right, direction and magnitude is what it's all about. So if an object's traveling at 65 miles an hour, the magnitude part's the scalar part, and then the direction really makes it a vector. So parts of a vector, there is a tail or a beginning, a tip or the end. That's where the vector's pointing. It could be a force, it could be a velocity of motion of a ball, or it could be a sailboat, it could be pretty much anything. It could be someone running the 100-meter dash. So again, magnitude's the length, direction. We usually reference it against a horizontal or a vertical line. So for example, if we have a ball traveling at 20 feet per second and it's initially hit at a projectile angle of 45 degrees above horizontal, it'll look something like that. Again, an object speeding along, let's say a car moving at 40 meters per second, that's about 85 miles an hour. So that vector is going to be twice as long as a vector representing that same vehicle traveling at 20 meters per second. There are two basic operations that we'll do. Vector composition, like that suggests, we're going to put two or more vectors together to make one net vector. In vector resolution, we're going to split up a single vector into perpendicular components. So that would mean like horizontal and vertical components. It's not always the case, but that's often what we do. When we're splitting up a muscle vector, one of the components will be drawn parallel to the bone. That's the part that actually usually, but not always, produces compression at joints and stabilizes joints and bones. There's another component that's drawn perpendicular to the bone that actually is the part that produces torque. So with vector composition, we're going to use a tip-to-tip method and a tip-to-tail method. Usually we'll put a tip-to-tail method when we're combining vectors, like combining forces, looking at the differential effects of wind on wind drag, etc. So with this tip-to-tail method, what we're going to do is, let's say we have two forces, and we want acting on a person, and we want to figure out the net force. We're going to move the tail of the first vector and touch the tip of the second, or the initial vector. So that means that we follow, imagine like a one-way street. And then you make a turn onto another one-way street. You don't want to go in the opposite direction. So that means that the two vectors, either the tips are touching or the tails are touching, we can move one of the other vectors. One of the advantages of vector operations is a vector can be moved as long as, you know, on a computer, on a piece of paper, as long as it has the same direction and the same magnitude. So I can move vector B wherever I want to. I'm going to move it so it touches the tip of vector A. Then the net vector goes from the beginning of the first vector to the end of the second vector. If there are three vectors, it gets a little bit more complicated. I'll show you kind of a shortcut way of dealing with three or more vectors in vector composition a little bit later on. Okay, so if the vectors are collinear, which means that they're right in the same direction with each other, if they are pointing in the same direction, the vectors that is, let's say we have two forces, a 100 Newton force and a 200 Newton force. Newtons are the standard units for force in the metric system. That's 1 kilogram of mass accelerated at 1 meter per second squared. So 100 newtons plus 200 newtons is equal to 300 newtons, pointing from left to right. Let's say we have two forces opposing each other. We'll have to give one an opposite sign. And we use the tip-to-tail method. We end up with a force vector traveling from right to left that's relatively small. 100 newtons traveling from right to left. We'll give that a negative sign just to indicate direction. If we're subtracting vectors, sometimes we want to take the difference. So a good example of that would be when we're using the fluid drag equation. And with the fluid drag equation, let's see if I can write it up here. Fluid drag is equal to 1/2 times the coefficient of drag times the area that's exposed normal or perpendicular to the wind times, I'm just going to type out rho. Rho's the density, and then the square of the relative velocity. Relative, not meaning a cousin or an aunt or an uncle, means the difference. So we talk about a relative joint angle. We talk about the difference between two angular positions. Here we're going to be talking about, let's see if I can do this correctly. Boom. Oh, yeah, there we go. So fluid drag is going to be proportional to the square of the relative velocity. So, for example, if the relative velocity doubles, the effect of fluid drag is 4 times as much. So, if we're sprinting into a headwind, and we're going to take the difference between these two vectors, we're going to subtract them. What we're trying to figure out is how fast the air molecules are traveling past that individual. When you're running into a headwind, you're colliding into more air molecules and having to push more out of the way. The more often you have to do that, or the more air molecules you move out of the way per unit time, the greater the amount of force. And again, it's a power function. It's related to the square of that velocity. So sprinting into a headwind, the air molecules are running past this individual who's going at 10 meters per second at 12 meters per second. So if we square that, that's 144. We'll keep that in mind just for a moment. If we're sprinting with that tailwind, so the wind is now in the opposite direction. By the way, a world record can only be set, I think, the wind, the tailwind, wind aided, we say. Tailwind has to be 0.5 meters per second or less, I believe. So 10 meters per second minus 2 meters per second, they're in the same direction. That's 8 meters per second. That's not how fast the individual is running, but how fast the air molecules are coming past them. So if we squared this value, right, because the fluid drag is proportional to the square of that velocity, that's 144 meters squared per second squared. And we do the same thing here. We've got 64 meters squared per second squared. Okay, so 144 versus 64, that's about 2.5 times as much air drag. Now that's significant for a runner, and this might be a runner or sprinter, because about 10%, maybe a little bit more, of the energy they use is overcoming fluid drag. For a cyclist, because they're traveling at a faster speed, it can be 25% of the energy that they're using is overcoming fluid drag or air drag. Sometimes instead of collinear vectors, we might have vectors at right angles. The advantage here is we can create a right triangle, use sine, cosine, tangent, or the Pythagorean theorem to solve for the net, depending upon what information we have. So I've got two vectors. We're trying to tackle Isaiah Spiller, and one player is pulling on him at 200 newtons, and a second player is pulling on him at 100 newtons. It's not actually a lot of force. And they're acting at an angle of 135 degrees from vector A. What we want to do is calculate the resultant or net vector. So what we're going to have to do is move one of these vectors, probably going to move vector B, move one of these vectors so that the tail of that vector touches the tip of the second one. Ah, there we go. Then the net vector will be from the beginning of vector A, which was 200, to the beginning of vector B, which was 100. And once we do that, we have to keep in mind that we started at this 135-degree angle. When we move vector B, theta, which will now be inside that triangle, is the complementary angle, meaning we take 180 degrees, that's half a circle of rotation, minus 135, and so that's going to be, looks like a 45-degree angle. So we've got net C, we've got side A and side B, and theta is opposite side C. Looks like the law of cosines to me. So that's what we'll do to solve this particular problem. So when we crunch the numbers out, we've got 200 squared plus 100 squared minus 2 times 100 times 200 using the formula above. So again, it's the Pythagorean theorem and a correction factor for the fact that this angle theta may be less than 90 degrees, maybe exactly 90 degrees, or maybe greater than 90 degrees. If it is 90 degrees, the cosine of 90 is equal to 0, and that term would disappear. So we crunch the numbers out, we get 147.4 newtons. That's the resultant vector. I could use the law of sines and solve for this angle, which would be beta, if I wanted to do that. And so here's how I set that up. Remember, any side divided by the sine of an opposite angle, that ratio is going to be the same for any other side divided by the side of its opposite angle. So I'm going to set this up and calculate beta because I know side C, I know theta. So the sine of beta, a little bit of algebra and trigonometry. I'm going to move the sine of beta over, divide by side C, multiply by the sine of theta, multiplied by B. And that gives me 100 newtons times the sine of 45 divided by 147.4 newtons. And that's 0.480. So I'll hit in my calculator. Here's my calculator. There it is. Hit my second function, sine, boom, inverse sine, and get 28.67 degrees. Just keep in mind on your calculator whether you're using degrees or radians. So it's 28.67 degrees above player A. Okay. Vector resolution is where we split up two or more vectors. So if I have a tow truck that's being pulled up, we have a vertical component and a horizontal component. So this is the actual force, and we've split it up into the horizontal component, taking the truck forward, and the vertical component lifting it upwards. So a long time ago, I used to travel from Louisiana to Georgia, and my car would break down. It was a Ford quite often. And so it seemed like I would always finish the trip like this, being pulled from behind back to the garage. Okay, so vector components, they can be horizontal or vertical. but they don't have to be. The point is they're going to be at a right angle. So we can actually draw a parallelogram where we have the tip of the horizontal component or one component of the net vector and then the other component. They'll always be at a right angle. That allows us to be able to construct a right triangle and use right triangle trigonometry. So here's my vertical, here's my horizontal component. Again, I can move a vector anywhere I want to as long as it has the same direction and magnitude. So I'll move the vertical component over here. Pretty good. Now that allows me to use sine or cosine. If I want to find the vertical side or the side opposite theta, then I'll use sine and cosine if I want to find the side adjacent to that angle theta. Now here's another example where we will use vector resolution. It's splitting up muscle vectors. So muscles can walk and chew gum at the same time. When they contract, they're usually contracting at an angle so that we can actually split up two different roles for the muscle looking at the vectors. So there's one vector that produces rotation. It's always drawn perpendicular with the lever or the bone or the body segment. So the elbow flexors, for example, are pulling up, and they often have what we call an angle of pull that's a lot less than 90 degrees. So when we resolve this vector, this is our rotary component. This is the one that produces torque or turning, elbow flexion in this case. And then we have a stabilized component. If alpha, or the angle of pull, is less than 90 degrees, it's going to be pointing towards the joint, actually pressing it together. Pressing forces resist against shear forces. If you press your palms lightly together and rub them, it's pretty easy if the amount of compression is small. But if it's high, and you can think about the palms of your hands as being like cartilage, then it becomes really, really tough. Oh my goodness. So that's one of the most important things that muscles do. They press our joints together, especially when there's a co-contraction of agonist and antagonist muscles. Biceps brachii, brachialis, brachioradialis on one side, triceps brachii on the other side. They're pulling that ulna into the humerus as well as the radius and maximizing that compression. And having some soft cartilage, good cartilage, joint cartilage as well as fiber cartilage, helps to provide a nice tight fit and really maximizes the contact area and really ensures or reduces the risk that a shear force could damage that joint. Those muscles are producing really large forces, partly because we have a lot of third-class levers, and some of the first-class levers that we have also require that you produce a lot of force. So they're large pressing forces. To lift a 20-pound weight in elbow flexion, it's going to take 200 pounds or more of muscle force probably to do that. Okay, another example where we resolve vectors are projectiles, in which again we're going to use an X and a Y component. The Y component is important because this vector is affected by gravity and the X component is not. So if we're shooting up towards the goal, producing that nice high arc, remember, you need that 50-55 degree angle. And then into the bucket, that Y component is changing at a constant rate due to gravity, 9.81 meters per second squared in acceleration, 32 feet per second squared in the English or SAE system. When we have vectors that, let's say we have 3 vectors or even more that we want to be able to put together, here's kind of a shortcut way of doing that rather than doing one by one by one. So in order to, let's say, combine, let's say 3 forces, 1, 2, and 3 here, what we're going to do is resolve each of these vectors into their horizontal and vertical components. So you do that for vector 1, for vector 2, vector 3 is pointing down, so you've got the Y component down, the X component back. Then what you're going to do is add all 3 vertical vec components together, the Y components, and all 3 X components together. Once you do that, then you create a net vector from the sum of the x components for that velocity and the sum of the y components for that velocity or vector. And once you do that, you can solve using right triangle trigonometry. So that's a really good way of doing it. When you have 3 or more vectors, you can do it with 2 vectors as well if you want to. Whatever gets you there, you'll end up with exactly the same results as if you used our vector composition and used the law of cosines or law of sines. So more than one way to be able to do that. So here's an example where we calculate the rotary, that's the part that produces torque, and the stabilized components of a muscle force. Let's say that we have a muscle force of 300 newtons. We can find the rotary force by multiplying 300 newtons times the sine of 37 degrees. That's 180.54 newtons. And this will be for an elbow flexor group, for example. And then we'll multiply that 300 newtons times the cosine of 37 degrees. That's 239.59 newtons. Okay, the important thing to see here is that each component is not 300 newtons, considerably less. The other thing to see is that this stabilized component, it's pointing towards the joint, meaning we're pressing those articulating bones together. B, look at the magnitude. It's larger than the rotary force. This is what happens most of the time, but not all of the time in the body. Because it doesn't happen all the time, there's often co-contractions, especially in your lower extremities. So at the knee joint, when you're exercising, you always have contractions of the quadriceps group, hamstrings group, and the gastrocnemius. Most people forget that the gastrocnemius, the primary plantar flexor muscle for the ankle, also crosses the knee joint and actually contributes to knee flexion. That means when the knee's extended, it actually stretches this muscle and it actually helps that muscle to contract and stabilizes the knee even more. So your calf muscles, hamstrings, and quadriceps all protect the knee joint. It's critical, especially when someone is at an injury to a major ligament and is going through rehabilitation. And as people get older or suffer from neuromuscular disease, we need to be able to remember that as well. So again, with vector resolution, we can split the vector up into X and Y components, or with a muscle, a component that is drawn parallel with the limb or the bone and perpendicular with the bone for the rotary component. So we can calculate, for example, X and Y components fairly straightforwardly using sine and cosine. Okay, so that will do it. I told you this would be short. This is our mini lecture on vectors. And so now we can apply them to velocity, acceleration, all the applications we're going to talk about in exercise biomechanics. So we'll see you next time.